off to the side. All right, everybody, thank you very much for coming to our very first workshops open day. My name is Jackson. I'm the coolest one up here. And yeah, let's get right into it. So first of all, if you are doing the ACM like attendance code, the attendance code for this event is OpenLobster23. Yeah, I'll leave that up for 10 seconds if you guys want to fill it out.
Does anyone not know what this is? Raise your hand if you don't know what this is. Okay, we have a few confused hands. Okay, I'm just going to give a quick explanation. So if you go into members.uclacm.com, this is something that we're kind of like rebooting this year. That is ACM wide. You can basically create an account, aka log in with your g.ucla email. And what happens is every single person here has an ACM account, if you will. And all that is just whenever you go to any ACM event, not just AI, you go to Cyber, Studio, Hack, whatever event, we will have an attendance code. And if you put in the attendance code during when an event is happening, you'll get some points. And it's just a little fun competition to see who has went to the most events. And that is all it is. We do put this up in case anyone does want to participate in this leaderboard thing.
Are there prizes?
I hope there are prizes.
Whoever shows up the most, Jordan will make them dinner. Yes. The code is not working.
Okay.
We will troubleshoot that and get back to you.
And try
Is it lobster or lobster?
I have
like
no idea.
open lobster. Try that. Sometimes the code is a little janky.
Open lobster.
No? Cool.
All right. We will troubleshoot this, and then at the end of the presentation, we will let you guys know what the code really is. Sorry about that. This is also our first time using the codes this quarter. So yeah. All righty. So to start things off, what is Open Day? Why are you guys all here? Well, basically, we are doing this event as a way for you to gauge what workshop might be appropriate for you. So we are going to be throwing a bunch of terms at you real quick, right? We're going to be covering the bare bones of what we cover in both tracks. Now, these are several weeks long, and usually each meeting is like 1.5 to 2 hours. So we're going to be going really fast. So do not worry if you don't catch it all. When you show up to the actual workshops, we go into much more detail. But if you don't understand any of what we are going to be presenting, that's totally fine. Our beginner track is the place for you to be. If you're looking at the beginner concepts and you feel pretty solid on them, but maybe the advanced stuff we go over is a little shaky, then advanced track is probably where you want to be checking out. Finally, if you're a whiz and you've got all of this and you're like, I don't even know why I showed up, we have our projects in our reading group, which are perfect for you. So with that being said, I'm going to go ahead and introduce the team. I'm Jackson. I'm right up there. You can see it's a very flattering selfie of me. We also have, do you want to just rattle ourselves off?
I'm Venkat. I'm going to be teaching beginner track.
Hey everyone, I'm Wade. I'll be teaching advanced track.
And Spark, I'll be teaching advanced track.
My name is Eric. I'll be doing beginner's track.
And then Claire and Naman are not here. You might see them around, but don't worry about it too much. Who did I skip?
Hi everyone, I'm Gregor. I'll be teaching the beginner track this quarter.
I'm sorry, Gregor. So do not panic, all right? Like Hitchhiker's Guide to the Galaxy when they're like, don't panic. Well, maybe you don't. Machine learning can be really daunting, but we've got you guys, all right? We're here to walk you through everything that you're going to need to know. So before we get into the actual different tracks, we're just going to do a quick little preamble about what exactly AI and ML is. So AI is really a very abstract concept, right? Anything that you're doing with your computer that would normally require a human to do, but you're doing with a computer instead, can be classified as AI, right? So, this includes like the really like flashy AI nowadays, but also by like some definitions, you could say Google Maps is AI because before computers, well, you needed to come up with like your own route to campus and stuff like that, right? And so this encompasses a lot of things. So what we're focused on is actually machine learning, which is a specific type of AI. And the basic concept here is that we're going to be taking our computers and we're going to be getting them to do AI tasks without like explicitly programming them to do something, like if you've written code before, you probably know that you go in and you're like, all right, I'm going to start off and I'm going to, make a loop. And then at each iteration of the loop, I'm going to like check for if some condition is true. And then you go through and do that. That is not what ML is. With machine learning, we are not writing all the code. We are essentially teaching the computer. Now, why is it important? AI really important. I'm sure all of you guys have cheated using ChatGPT. It's well, maybe you're better than me. But all aspects of our life, not just cheating on schoolwork assignments, are being impacted by AI. Very soon, it's going to be practically impossible. In fact, now it's practically impossible to name an area where we do not see the effects of AI and ML. So some examples include, ChatGPT, but also things like, language translation, Google Translate, cancer detection, image recognition, Siri and Alexa, stable diffusion, which is like the AI art that you see, all sorts of stuff, right? Now, you may have heard me say model up here. And basically, when I say model, I don't mean a really attractive person who walks down a runway. I mean something that takes in some input and then it produces an output, right? So it takes in a picture and then it tells me if it's a picture of a cat or a dog, right? Or it takes in an English sentence and outputs a French sentence, right? And so machine learning helps us create really good models through a process that we call training. And there's two big ways that we categorize our models, which is continuous or categorical. So continuous, if you guys remember, like your math, is basically there's an entire spectrum that an infinite number of options, usually with like numbers. So like if you're outputting a number between like 1 and 10, that's like continuous, right? Because it can be any number of decimals. Or categorical, where you're like, is this a cat or a dog? And it's like one of two things, right? And then finally, we've got a bunch of types of machine learning models. We'll be touching on most of these, and don't worry if you don't understand it yet. We have supervised and unsupervised learning, semi-supervised learning, so lots of supervision going on, and then reinforcement learning. There's more types, but just a quick little peek at what we might be touching on soon. And finally, before we get into the actual workshops, the pipeline of machine learning that we are trying to get you guys all familiar with is as shown up there. We're going to be talking about data preparation, because in order to make your models work, a little spoiler for you guys, you need a lot of data. So you have to take that data and get it ready to use. Then you need to feed it into the model. You have to see how good your model is doing. That's the calculate loss part. And then based on how good your model is doing, you can change it so it does even better. And then finally, after you've done that and you have a pretty good model, you're going to be working on validation, which is basically being like, all right, I think this is really good, but I actually got to test it. And then once you've done all that, you're like, perfect. I have, the world's best, I don't know, like program at differentiating cats and dogs, right? And then you would deploy it, which is just put it out there into the world. So now I'm going to hand it over to our wonderful beginner track officers. Give it up for them. Woo!
Okay, cool. We're just going to cover a little bit of the beginner track content. Beginner track is going to focus mostly on classical machine learning and simple introductions to the maths behind it, including an introduction to Python. Python is one of the premier languages for statistics, data science, and any form of machine learning and data processing. It's got a really clean and clear syntax. It's very beginner friendly. I'm sure most of you have worked in it at least a little bit before coming. The main reason that it's used is not necessarily because it's a fast or very efficient language. In fact, it's relatively slow, but rather for the number of libraries like SciPy, NumPy, sklearn, pytorch, and TensorFlow that all support machine learning and are cross-compiled into other languages to run much, much quicker than Python can. Throughout the quarter, we're going to be doing code-alongs and notebooks. All of those will be completed in Python.
So the next part is we're going to be speed running through a bunch of different terms. So we're just going to talk about what these terms generally mean. We're not going to go into the math behind any of these terms or anything like that. So as Jackson had mentioned in the beginning, if you feel comfortable with these terms, you guys can check out the advanced track content. If you want to know more about the mathematical derivations or you don't feel too comfortable, then you can always come to beginner track. So the first term we're going to talk about or model is KNN, K nearest neighbors. So basically the idea for this is you have a bunch of different points and you want to classify these points into different groups. So in our example right here, we have two classes, the triangles and the squares, class A and class B. And the idea is you want to divide these. So draw like maybe a line that separates these two groups. And so the way we do that is we want to measure the distance to a certain point, and then we can classify them as such. So that involves using the distance formula and creating the groupings like that. So the math of that is covered in beginner track. So that is the first one, Kist Neighbors. The next one is linear regression. So most of you will know this one as finding the line of best fit. And that is literally what it does. So you have a scatter plot and your goal is to find the line of best fit. So one example that we generally like to use, okay, this one is using the grade you're going to get on a test. So we can run with that example. So you have a bunch of different factors. So amount of sleep, the time studied, your past grades, and how often you go to class. I personally don't go to class, so that factor is a little lacking. But you can create a linear regression model to predict, given all these inputs, what your grade on that exam will be. And so that is one example. And so, as we said, linear regression. So we're basically dealing with a linear equation in the most basic sense. And so right here, we have y equals x is equal to b, which is just a bias. So in a two-dimensional world, that's your intercept, your y-intercept. And then for each of our inputs, we have different weights. So let's say you keep skipping class, but that's not affecting your grades. We may put a little bit of a lower weight to that. Let's say, we see that you've gotten really good grades before, even though you've not studied and you've got 0 sleep the night before, we may put an increased weight to that. And so that is basically how linear regression works, right? How do we figure out those weights? Those weights are what optimize that line, the line of best fit. Okay. The last one we're going to cover is logistic regression. So linear regression, if you think about it, only works with continuous data, right? So your test scores are between 0 and 100. Suppose you're trying to predict house prices. That's a dollar value, right? Like anywhere between 100,000 to like 3 million if you're from the Bay Area. So it's all continuous. But logistic regression works with categorical data. So let's say you want to identify whether something is a dog or a cat, right? There's no in between a dog and a cat. This is 1.25 dog, 0.75 cat. Please let me know if you've seen something like that. That is mildly concerning. But so what we want to do is we say a dog is 0, a cat is 1. Logistic regression. We have 2 distinct categories that we're trying to identify. So logistic regression is similar to linear regression in many ways, but having categorical makes it a little bit difficult. So how do we deal with that? We use something called the sigmoid function. And you can basically think of the sigmoid function as a function that goes something in between 0 and 1. And we don't have a picture of it on here, but it basically looks something like that, where this is your axes. So this is 1, this is 0. And basically what we can do is we can map everything to a value between 0 and 1. And this will be like our probability that something is 0 or something is a 1. So we're still getting a continuous value, but we can map that to a categorical value. And then we optimize for that. And so that is logistic regression. And that awful function I drew on the whiteboard is this, 1 over 1 plus e to the power of minus x. All right. So those are like the big concepts we're going to be covering in beginner track. I think that's like 3 or 4 workshops. So it's a bit of time. We do cover like more derivations and stuff like that. But if you're feeling good about all these terms, you're probably good to go to advanced track.
Yeah. And actually, there's one more thing we cover at the end in the beginner track, which is we actually give you a little preview of what advanced track is like. And we start with motivating something called neural networks. Who here has heard of the term neural networks before? Oh yeah, we see a lot of hands. So Raheel is going to help us motivate what that is, starting with the artificial neuron.
Hello. So an artificial neuron is basically like the connecting point of a neural network. It's essentially the fundamental building block of a neural network. The way it works is it takes in an input or multiple inputs and multiplies it by the weight, which is the parameter that's trained in a neural network, and it adds it to a bias, which is also a parameter that's trained in a neural network, and it puts all of this through something called an activation function. Now you might be wondering, what is this? Where does this come from? In nature, of course, and it comes from a model of our brain. So if you take every single neuron in the human brain, it loosely follows this. So it has a certain amount of inputs, and then through some type of time delay or so on, it activates, or the synapse is activated, and the signals propagates through the neuron. So this is loosely modeled from the brain. And in addition to that, I think one really good way to think about this is like a bunch of switches. So when you have a bunch of nodes that work together, you essentially have a bunch of switches and light switches, and you can essentially make any image you want or any sort of output you want. It's basically sort of like a function generator. That's a good way to think about it.
And if you kind of look at this a little bit more carefully here, we see that we have a bunch of inputs. They're all weighed by a bunch of sort of parameters that we train, and we have a bit of bias. What does that look like? We just saw this actually. It kind of looks like something we just seen. It kind of looks like linear regression, right? So what it really is neural networks are almost like a multi-layer generalization of what linear regression and logistic regression are. And we can actually see it over here.
Yep. So to give you guys a brief overview of what a neural network is, so I'm guessing you guys have definitely heard of neural networks before. Like you have ChatGPT, you have a lot of reinforcement learning models, like the model that beat the famous chess player. So essentially, a neural network is a group of machine models that are loosely inspired by the brain. And in the focus of these neural networks are essentially nodes that are connected, as you can see, in layers. And each of the layer takes in an input and outputs an output based on certain calculations that are made inside the node, multiplying it by a weight and adding a bias. And after which we have an output to which we compare it with a labeled output, and through the process of gradient descent, we go back and update all the weights. So essentially the way I think about it is it's a gigantic structure. We feed it an input, it takes in an output, and then we update the parameters. So that's a very simple way of thinking about it. And don't worry if it's a little bit complicated now, we'll explain it all in the tracks.
Yeah. And another way I think that's really nice to think about neural networks is essentially we have, if this is a single artificial neuron, we can think of neural networks as just a bunch of artificial neurons that are kind of stacked with each other. Like you can kind of, like you can see how the first three kind of feeds into the first one. That's one artificial neuron. The first three also, by different weights, feeds into the second one, the second layer. And that's another artificial neuron. It is a densely connected artificial neuron, which is also a term that you may have heard before, densely connected layers. And that's basically what it is. We're taking the idea of artificial neurons and pushing it to the max. And the reason why we can do this, because this seems awfully computationally expensive, doesn't it? We have a lot of calculations that's going on, is because all of these can be simplified or abstracted or written as matrix multiplications. Who here has heard of the mathematical term matrix before? Okay, we have a lot of people who have heard of it. Yeah, so for those of you who don't know, it is essentially a grid, a 2D, generally, grid of numbers. And it follows some sort of multiplication rule that actually exactly aligns with how neural networks work. And that's how neural networks are actually implemented almost 100% in every single place nowadays. It's via matrices. And the reason why we implement them via matrices is because our computers, specifically our graphics cards, are really, really, really good at doing huge matrix multiplications. And this is why you may have heard of, like ChatGPT being trained on, tens of thousands of, extremely expensive GPUs. Why GPUs? Is because they're really good at what we need them to do. Does that make sense? Okay, cool. So now I think it's time for us to move on to what we really teach in advanced track, which a lot of it surrounds the idea of something called deep learning. And before we continue, I want to tell you a story of how deep learning came to be in the first place. So deep learning actually only became really something that machine learning scientists were heavily considering in 2012, which is 11 years ago. And it sounds kind of crazy, but basically what happened before was there was a lot of challenges that was there with training deeper networks, where we had problems of trying to make sure numbers didn't get super duper small or explode to really, really large. And there were several, and it was a really influential 2012 paper called AlexNet that solved a lot of these problems. Now I'm getting ahead of myself. We will talk a lot more about this in advanced track, specifically on our second or third workshop on CNNs, but that's how deep learning came to be. Someone figured out a way to say, hey, we can train deep networks now. And it worked so well that scientists started experimenting with deeper and deeper and deeper networks to today is, we don't know the number of parameters for ChatGPT, but for example, for stable diffusion, there is 1.4 billion parameters in the model. For Llama, which is Google's open source version of ChatGPT, has 77 billion or even hundreds of billions of parameters. The reason why it is possible is all because in 2012, some people figured out, hey, here's how you can do deep learning. But with that in mind, we've been talking a lot about neural networks and about, like, oh, we have some sort of inputs. We do a bunch of mathematical operations to arrive at some sort of output. But how do we actually train this network? How do we know, for example, this weight over here is 0.45 and that weight is 0.6? How do we arrive at those numbers? We've been throwing around the word gradient descent a lot, but when I first started learning machine learning, it was a little confusing. So I want to kind of motivate all of that. So how does a computer know how well a model is doing? Because to be able to say, let's improve the model, computer improve the model, computer make the model better, we have to have some way of measuring how well a model is doing. And the way that we measure it is something called a loss function. A loss, an objective, a residual. People have many different names for this thing. And in this case specifically, the lower this value is, the better the model is doing. And an example of this loss function you can think about is something called the mean squared error, which basically you have the model outputs a vector. You say this is, and you have a label vector, aka we say the vector that we want the model to output, and we basically find the error between them. And you can kind of see how if we are lowering the error, the model would be doing better, aka the model is outputting what we expect it to output. And that's what the role of an optimizer is. An optimizer tries to lower a model's loss by essentially nudging the model weights around iteratively and hoping that we're going to arrive at a good enough local minimum. And what do I mean by local minimum in this case? So I want you to imagine, if you recall to what I was saying before, with neural networks, what we are calling the network itself is the weights of the network, right? It's the entries of the matrices, it's the entry of the bias. And what we can do is we can think of all the possible values of those entries, each entry as a separate dimension, this really high dimensional space. It's difficult to imagine, but I will start with a neural network that only has two variables. We can kind of abstract it out and just say, oh, we have this neural network that has our first weight and our second weight, f of w1 and w2. Right? We have two weights that dictate how this neural network takes in an input and outputs something. And we can imagine the possible values of this w1 and w2 as kind of like our x and y axis, our horizontal axis, right? All the possible values of w1, all the possible values of w2, and our z axis, our vertical axis here, as the loss function. And you can kind of see how our goal then becomes, where on this, what we call loss landscape, is the loss the lowest? We're trying to find the global minimum. Does that make sense, what's happening here with optimization? This is, anyone who's like a little bit, okay, I'm going to continue then. So we first initialize neural network models by picking a random point on this loss landscape. And because we just picked a random point, it probably isn't a very good point. And our goal is then to say, we're going to nudge this neural network model, which is really just a point in a really, really high dimensional space. And we're going to try to find a global minimum. If not, because a lot of times when we have billions of parameters, the space is a billion something dimensions. That's really hard. So just a really, really good enough local minimum. Does that make sense? Okay, so the way we do it is via something called gradient descent. So what a gradient is who here is currently taking Math 32A? Okay, we have some people taking Math 32A. Have you guys covered gradients yet? Mention it? Okay, so in short, what a gradient is basically you have a neural network, you have your loss. You're basically taking what we call a partial derivative of the loss with respect to every single entry of the weights. So you end up with a vector that is exactly the same dimension as your weights, right? What the gradient is it calculates the direction of greatest ascent. So for example, if we have, I'm trying, okay, let's say we have this object here, right? And we have a point over here. Which direction do you think the point should go so it goes up by the most? Towards me, right? Towards this direction. And that's what the gradient calculates. If we say take the gradient vector and just plot it on here, it's going to point this way. So if we can find the direction of greatest ascent, aka where we can nudge the model so the loss increases the most, we want the opposite of that, right? We want the loss to decrease the most. So what do? Now we have this gradient. Nudge it in the negative direction. right? Which is why we call this process gradient descent, right? We calculate the gradients and we say and we say nudge the model in the direction which will minimize the loss the most, at least in that local framework that we have. And that's what gradient descent is. We do this process iteratively. And sometimes, with different amounts of data and things like that, this may be an unstable process. So we may have, like an alpha term here that's like 0.01 to dampen that process and to slow that process because we want to see a bunch of data before, and do this iteratively. But that's how generally almost every single neural network model nowadays learn. We calculate the gradient and we say, now we know the direction to nudge this model so that it is going in so that at least in this local view of gradients, our loss is going to be decreased the most. And we do this iteratively, tens of times, thousands of times, tens of thousands of times. And hopefully, we're going to get to a good global minimum. Does all this make sense? Okay. Again, this may be a lot, and we're going to cover this in more detail on the advanced track, but this is the basic idea behind how neural networks learn. Any questions before I continue? Yes.
Do you recommend having taken like your today for like going to the next track?
No, like this is basically like the maximum amount of math we're going to cover. Like the other math that we are going to talk about is chain rule. Who here has heard of chain rule? Yeah, okay. So yeah, we're gonna talk about chain rule, and like that's pretty much all you need. We're gonna mention some matrices, but like you're never going to be doing this math manually because the amazing thing is like PyTorch does all of this automatically for you. But we still want you to understand this is how it actually works behind the scenes. Yes.
I'm 32, 31. Is that gonna work?
No, yeah. You don't have to be taking anything to me here. Like we're going to introduce everything like from scratch. Like I think the only quote thing you need is have a general idea of what calculus is and what a derivative is, and that you should be good. Like if you want to delve into the math, like that's something you're totally open to do to find us after like our workshops or even after this. But like you don't need to have math prerequisites, except I vaguely know what calculus is. So that's kind of what I'm putting out there. Okay. Awesome. Cool. All right. One last thing is I want to talk about how do we actually calculate this gradients. I'm not going to go into a lot of this, but the idea is that neural networks are a bunch of just functions after one another, really small rudimentary functions after one another, mixed multiplications and stuff like that. And these are functions that are simple enough that we can calculate the derivatives. And if we have a bunch of functions that's composed after one another, what is a good way to find the derivative? The chain rule, right? And that's basically what we do. Backpropagation, the calculation of how to calculate gradient is just really, really, really annoying chain rule you have to do. The computer does most of that for you. It's a lot of matrix multiplication, but that's all it is. It's chain rule. And with training neural network models, that is 90% of the time, even more, 95% of the time is spent calculating this damn gradients, right? That's what you're mostly spending time doing. So that is what we really mean when we say we optimize for the loss, we optimize for the network, we're going to train this network. This is, on a very broad view, what's happening behind the scenes. So now with that in mind, let's go on to some different neural network architectures that are used today.
All right, so the first kind of neural network that you're probably going to hear about is something called the fully connected neural network, which has the input layer, a series of hidden layers, and then the output layer. However, there is a small problem with this kind of design, especially when it comes to image recognition. So one of the issues that'll come up is the thing you might be trying to identify might appear in different points in the picture. So it could be in the top right, bottom left, whatever. A fully connected neural network does not do well with this. However, we present the CNN, aka cable news network, or convolutional news network. Or really, okay, let's just say what it actually is, the convolutional neural network. So it's a type of neural network that does really well with data used, basically spatial data. So for example, in images, there is the X dimension, the Y dimension, as well as the color. Because a color is actually, it's represented as a vector.
RGB.
Yeah, exactly, RGB. RG, yeah, each of those, that's 3 dimensions right there. X and Y is an R dimension. And so this is why a CNN is really good. And some of its widely used applications are for obviously image recognition as well as computer vision. So one of the most important things is self-driving cars. So to go back to my point about the location of something in a picture, that's really important for self-driving cars, because if you think you see something somewhere different from where it is, you could wind up crashing your car. So it's really important that it works independently of position in the image.
And here's a little visualization of what a CNN layer looks like. As you can see, like as opposed to what we have with fully connected networks before, it's kind of almost like a filter that goes through the image.
Yeah. So the way it works is that we have a filter that is smaller than the image itself, and then through going through a filter through usually each pixel in an image, for example, it will extract the most important features. And then through a mathematical operation called convolution, do we teach it? We don't need to teach exactly what that is, right? No, okay. Yeah, if you take some math classes here, you'll learn what that is exactly. Basically, it just teaches you the relationship between one function and another. Here, it's the relation between one pixel and another. And so then by doing that, we can extract the most important features of an image, and then we use a thing called pooling, which you'll learn more about in advanced track, to basically put those together, and then that layer that basically says, okay, here are the most important features in the image we've just fed through, and then we then feed that into a fully connected layer, and then after that, it's just a regular neural network. And so now another type of neural network involves a little bit of a different approach, but let's go talk about it.
All right, I'm back. So as we've been discussing, the neural networks are really, really good at handling mathematical input in the form of vectors. However, what if you want to work with words? What if you want to generate words or process words to try and predict some attribute about them? In that case, there wasn't really any way to handle them until we decided to start using something called embeddings. Essentially, we learn a way to categorize and create vectors for words corresponding to the traits that a word has. So in this example, the king vector and the man and woman vectors are relatively similar. The man vector is likely going to be in some way similar to the king vector will be likely similar to the sum of man and royalty, or some other concept such as that. Essentially, each individual component within the vector will correspond to a certain trait that a word holds or that an object has. And now back to, I think it's sparse up next with recurrent neural networks.
So as we saw earlier, right, with CNNs, you have this special architecture to deal with image data. So similarly to that, we have a special kind of architecture to deal with time series data, and more specifically languages and like language models. And so as you can see from Gregor's previous slide, what we did was we took our words and we converted them to numbers, to a vector of numbers, which is great. And now we can use this as the input to our subsequent models to analyze what these exactly mean. So the first kind of language model we'll be talking about, or just time series model in general, is the RNN, the recurrent neural network. And so basically, essentially the RNN is just this structure just chained together multiple times. So what you do is you have some input, you multiply it by something from the hidden layer, something that describes the previous word, for example, and then you run that through another fully connected network, and then you get your output. And the current word that you get will then inform the next round of the hidden layers. So then the next word comes in, you put your hidden layer information again, and then from that you get another output, and so on and so forth. And you just keep repeating it until you get to the very end. So one problem with RNNs is that they're not super great at taking long-term trends into account, because the hidden layer is just informed by what the previous layer was, or the previous word was. And we might want to have some trend that takes long-term memory into account. And we might want to modify that memory because maybe some things in the past are more important than other things. And we want to have that sort of weighting into account. And so for this, we have a modification of the RNN architecture, which is called the LSTM, which stands for long short-term memory, which is kind of a contradiction in terms, but whatever. So similar to RNNs, but they have the ability to remember this information. And that is done through what is called the through the self state and the hidden state memory. So the idea is that every time a word comes in, you put it into, you make a decision as to how much you want to remember the previous information or how much you want to forget the previous information and how much you want to remember the current information. And you put that into a cell. And so that way you can remember this better because it sort of encompasses all of the data that you've looked at from the past, along with a measurement of how much you want to remember each individual thing and how much you want to forget it. And that way you can sort of keep track of long-term trends into account. Of course, if you have a lot of data, still stuff that's from very, very early on is still going to get like depleted, right? Because if you keep forgetting it a little bit, eventually the earliest stuff is just like gonna go to zero. So this doesn't address the problem completely, but it does go a long way in sort of solving it because you now have this concept of long-term memory.
This thing's stuck. There we go.
Okay. So now we go to transformers, and transformers are much, much more complicated than RNNs and LSTMs. So I'll just like sort of go through their architecture a little bit quickly. If you want some more details, you can always come to the advanced track session on these things.
Fun fact, this is the backbone of almost every single modern, as in after 2017, large language model, including ChatGPT. You may have heard of BERT, T5, all these things. This is what's powering all of them. These are what makes up their layers.
Yeah. So they're like very, very different, but because they have a power in their structure that you don't get with RNNs and LSTMs. And what that lets you do is let you make much, much more powerful models. And you can use this, for example, I mean, the most commonly used example is for translation, where you take some input text, say in French, and you get English, or vice versa. You put something in English and you get something in French. So the way that it works essentially is that you take your input, you pass it through a stack of what are called encoders, and I'll get into that in a moment. And then that stack of encoders is going to yield a couple matrices. And those matrices are then used to inform how the decoder stack should work. So with the decoder stack, you'll output some token, let's say a word, and then that word will then be used to generate the next one through the decoder. And that, again, is going to be informed by these matrices that are the outcome of the encoder. So looking at it in a slight bit more detail, what you see is something called self-attention. And like, I could talk about self-attention for an hour just on its own, but I'll cut it short here. Again, more details, advanced track. But what you essentially do with self-attention is you take all those embeddings that we talked about earlier, and you sort of modify them so that now these embeddings reflect how much each word relates to every other word in your input. And so that's what the self-attention layer is going to do. Then you're going to like modify these to make sure they don't get too big or too small with the normalization. And then if you do that a bunch of times, now you'll get a bunch of new embeddings for everything. And you sort of just put them all together. And then that will be what you pass forward from one encoder stack to the next. And now you keep doing this. What I just described, do that again for the next encoder stack and the next one and the next one. However many layers you have for the encoder, you just keep sort of like modifying your data that way till you get to the very end. And you end up with this K encoder stack thing and this V encoder stack thing. And these two are going to then inform how the decoder should work. And again, you have some outcome from the decoder, say the word I. That word I is going to go back into the decoders, get pushed through the decoder stack again. And then you're going to get another embedding, which could correspond to the word am, and so on and so forth, until you get to a student, and then it tells you that's the end of the text that you want to work with. So in a very, very brief overview, that's sort of the way that the architecture of transformers works. So just to, oh, yes? So that is something to do more so with the embeddings that we start off with. But the idea is that when we're finding the embeddings for words, typically we'll want to do what is called stemming and lemmatization. So if there are some grammatical features that don't necessarily impact the meaning too much, we might want to sort of eliminate them, or maybe we will want to account for them in embeddings. It sort of depends on what the purpose is. But generally speaking, we'll sort of, if there's like a plural like S ending in English, for example, we'll typically remove it. But if it informs the meaning, then we might want to keep it. Yes. And that's to do with the exact same architecture as we had before, right? Where we pass something to the decoder stack, and from that next word, it predicts what needs to go next and next and next. And that's actually how the ChatGPT architecture works as well. You just keep predicting the next thing based on what you had previously. Okay.
Okay. Oh, and one more thing I do want to add about like these, what we call kind of time series or like sequential models, is a good way to think about them is, as opposed to just our weights being the weights that there is, what they try to do is they try to use your inputs to almost generate new weights that will then affect the same weights itself. So it makes it a little bit more adaptive to, say, the content that comes before or context and things like that. And that's why these models are so powerful. And again, if any of these sound confusing or like it sounds like it's a lot, we're just throwing information at you, that's kind of what's happening. We're trying to give you a feel of this is what we cover in workshops, and we're hoping that this can allow you to make an informed decision eventually. But now I want to spend a tiny bit of time talking about generative networks for vision. And specifically, the very first one I want to talk about is something called generative adversarial networks. So the difference between like what we had before of classification networks, which is we put in an image or a word or something, and we want to classify it, right? We want to say this belongs to this class, this belongs to this class, or we're trying to predict something about this original picture. With generative networks, we're putting in nothing, or at least a very small amount of information, such as this is like, like a picture of a horse on the moon, for example. And we're trying to then generate, say, an image out of it. And particularly, the way the generative adversarial network works is you actually have two networks who are competing with each other. You have something called a generator and something called a discriminator. The generator, its job is just to generate images. It generates images from some pure noise, and that's all it does. And it does so by basically using what we call an inverse convolution. It takes some noise and basically kind of starts blowing it up using a bunch of inverse convolutional layers. Again, we'll get more into it in advanced track. And the discriminator has one job. It looks at, given a bunch of images, it's trying to figure out, is this image generated by the generator, or is this image from the actual real data sets? And and you can kind of see how these two models or these two networks have fundamentally like contradictory goals, right? One is trying to like suss out the other one, while the generator is trying to generate images that will fool the discriminator. And we're training these two networks at the same time, right? And with some careful tuning and with a lot of careful methods, we can basically train a generator that is, we don't say perfect, but theoretically speaking, it should perfectly match the distribution of images, aka the data set that we give it. And that's how GANs work. And that's how, has anyone here heard of the website thispersondoesnotexist.com? Yes. That is powered by a generative adversarial network, specifically something called a style GAN, which we will cover in a little bit more detail in both advanced track and in even more detail in in one of our reading groups about deep generative networks in the future. So then we move on to something called diffusion models. Who here has heard of stable diffusion here? How about AI arts? Okay, we have a few more hands. But basically, the diffusion model is what powers the backbone of a lot of these image generation models. And the reason why we moved on from generative adversarial networks is for a few reasons. You can kind of see how generator and discriminator, it may be a little bit unstable, right? As you're training it. Well, the diffusion model solves this issue by basically being something completely different. When you're training the model, all you're saying is, I have an image here that I've added some noise to it. Model, separate the original image and the noise. That's all we're training the model to do. And when we're actually generating an image, we're saying, I'm going to give the model a pure noise. It's going to try to separate the noise and the image. It's going to be very bad at the separation. But basically what we do is we say, we use this to denoise the image a little bit. Then we denoise it a little bit more. Then we denoise it again. We denoise it, we denoise it, we denoise it. And we just basically train a model that's so good at denoising that it is able to generate an image from pure noise. And that's how diffusion models work. And that's also why if you were saying playing with diffusion models on the internet, it takes like 15 seconds to generate an image. It's because it's doing this process over and over and over again, 50 times, 100 times, 500 times, depending on the specific model you're using. But that's the idea of how a lot of diffusion models work. And sometimes we add what is called a condition, a text condition, which is basically we help the model, we tell the model, oh, this is the type of image I want you to generate. This is what I want you to generate. And the way we're telling the model that is via text embeddings, which we have covered before. But text embeddings are very powerful. And I think diffusion models are really awesome because they're almost like this culmination of a lot of really great stuff we have in natural language processing and a lot of really great stuff we have in computer vision. But again, this was something that we will cover a little bit in advanced track and a lot more in one of our future reading groups. Be on Discord to keep an eye out for it when it does appear.
Alrighty, guys. So I'm going to be ending us off here. First of all, I just want to see who here understood everything we talked about tonight. All right, that's good. I'm not alone. I like most of this stuff. Like it's magic, right? So the good news is that means we got the right target audience. As we said at the beginning, the point of this was that you guys were not going to get all of it, and it would help you understand what you might need to learn from us. So one last thing we're going to touch on really quick is just PyTorch. Most of our projects are done in PyTorch. So if you know what that is and you're familiar with it already, that's going to give you a bit of a leg up. But again, like with everything else, we will absolutely be teaching you, and there's no prior experience necessary. And most of the conceptuals here is like done for us. Like remember all that talk about like gradient descents and stuff like that. Like as Jordan was saying, you don't have to do all that math. You just write one line of code, and then it all gets done for you. And yeah, that's an example PyTorch workflow. We don't really need to look at it that closely. So thank you guys all for coming. This was our very first open day. Woo! Yeah, give me some applause. Yeah. If you have a moment, we would sincerely appreciate any and all feedback that you can give us. Otherwise, we'll be hanging out around for a little bit. Feel free to come up with any questions. Also, Studio has a GM at 7:30. So if you like game design, stick around.
Yes.